Physical Science. This is Mr. B, and we are starting Chapter 6 today. And the title of this chapter is Chemical Bonds. And just to give you kind of a brief overview of what you might expect in this chapter, it's going to be about how different elements are held together in different types of arrangements. So there's going to be a bunch of different type of bonds that can form to hold different elements together in different ways. And one of the driving forces behind what type of bonds are formed are going to be based off of our valence electrons. And if you remember, we spent a lot of time with our different group A elements, counting the number of valence electrons that they possess, makes them more reactive versus less reactive. So that's what is going to be the driving force behind a lot of the ways that chemical bonds are formed. It's really going to depend on the number of valence electrons that an atom possesses. So to start, our first section is going to be about ionic bonding. So that's going to be the first type of bond that we talk about, is an ionic bond. And I don't even know if we'll make it to that in this video, but it will be brought up shortly. If it doesn't make it in this one, it'll be in the next one. So ionic bonding. So to start, though, before we get into any specifics of actual information, we have to get a little real-life example to help kind of introduce us to our chapter. So it starts by saying that the handle of this titanium mug was joined to the body by welding. At the welding temperature, titanium reacts with oxygen in the air, which forms what's called an oxide. So maybe you've seen like carbon dioxide and things like that, or carbon monoxide. We're going to learn in this chapter also what this IDE means. Hopefully maybe you can tell that the OX stands for oxygen. But one thing we're going to mention in this chapter is where these IDE comes from. What does that actually mean? But that's just to give you a little look ahead. We're not going to get there yet. And the oxide makes the weld more brittle. And then chemical properties, such as reactivity, depend on an element's electron configuration. So you might not have known this, but welding actually has to deal with the element's electron configuration. So some pretty interesting stuff here, but we will talk more about this stuff here in a little bit. The main thing probably is we're going to discuss the actual meaning behind these different prefixes and suffixes to actually help us understand what elements are actually showing us here. Now, to start, we're starting with stable electron configurations, and this is going to be kind of the ones that aren't going to want to form bonds, so we kind of have to start with the kind of the exception to the rule always. So when the highest occupied energy level of an atom is filled with electrons, the atom is stable and not likely to react. So if you remember the group 8A elements, we're going to see those in a second, with the exception of helium. Those are all very stable elements. Remember, those are the noble gases. The noble gases aren't going to form, or they have a very low reactivity. So they're very stable. They are happy the way they are, so they're not going to react too often. So that is kind of the opposite of we're going to talk about for the rest of this chapter, about how elements come together. Noble gases are going to be the ones that do not, because their atoms are pretty happy the way they are. And so one way we can take a look at the chemical properties of an element and by looking at the number of valence electrons, which we've talked about that before. So the number of valence electrons is going to affect the chemical properties, and this is a big thing, the electron dot diagram. So this is really big here. It is a model of an atom in which each dot represents a valence electron, and the symbol at the center represents the nucleus and all other electrons in the atom. So when we talk about an electron dot diagram, it's going to represent not all of the electrons, so that's a big thing. Make sure you write that down. It is not all of the electrons, it's only the valence electrons. It only represents the electrons in the outermost energy level. And we'll get an example here in a second. Actually, we'll just go ahead and do that now. So here are our main groups that we focus on, the A group elements here. So group 1A is what we're going to start with. So we're just going to fill it out as we go here. So hydrogen, lithium, sodium, and potassium all are in group 1A. Remember, all of group 1A elements have one valence electron, so they all have just one dot on the outside of them. Now hydrogen only has one total electron because it's the first one. Lithium has more, however, it doesn't have all of the electrons that's represented in lithium. They only have the ones in the outermost energy level. So lithium has one, sodium has one in the outermost energy level, and so does potassium. So I have a feeling that for your quiz, I might just give you probably this top part right here, 1A, 2A, 3A, 4A, 5A, 6A, 7A, and 8A, and then have you fill in electron dot diagrams accordingly. So hopefully maybe we can make a prediction for the 2A, how many electrons they're going to have. So you notice we have 1, 2, 1, 2, 1, 2. So again, these are not all of the electrons that these elements possess, or that these atoms possess. It's just in the outermost shell. And then 3A, hopefully maybe we can make a prediction of what the 3A is going to look like. Of course, there are 3. You notice how we don't match any of them up right next to each other. I guess just kind of a standard rule until we have to. So the 4A, again, hopefully maybe you could guess that they're going to have 4 dots, because we represent the 4 valence electrons in that group. 5A, 5, again, you can see 1, 2, 3, 4, 5. Again, that is not all of the electrons that each one of these atoms possesses. It's just the valence. 6A, hopefully you can guess, it's going to be 6 dots. 7A, 7 dots. And then 8A, remember we got to be careful on this one because helium is our one exception to the rule. Helium only has 2, and then neon, argon, and krypton, again, these are all of our noble gases. They're very stable. So they're not really going to want to react because, you know what, we're pretty happy the way we are. We like having these 8 electrons in our outermost energy level. And to wrap this section up of this video, it says noble gases are the most stable elements, which we just said. And the reason why is because the highest occupied energy level of a noble gas atom is completely filled. They have stable electron configurations with 8 valence electrons, which we kind of just repeating itself. And then elements tend to react to achieve electron configurations similar to those of noble gases. So this right here is one of the most important statements that really sets up the rest of this chapter. The reason why we're going to have any of these reactions that we're going to talk about here in the upcoming days is because elements want to achieve electron configurations similar to those of noble gases. They want to have 8 valence electrons. If you have 8 valence electrons, you're very stable. It's very easy for you to exist. You're not going to really react with anything else. So that is really, really important here. So make sure that you understand the basic rules for this electron dot diagram, that 1A is going to have 1, 2A, 2, and so on, and so on, and so on. And then this last statement right here is pretty important as well. So we're going to go ahead and stop for the first part of section 1. Let me know if you have any questions.